We're presenting CPU condition preference optimization for controllable image generation today. So we first introduce the task definition of the controllable image generation. So controllable image generation means that we're given a input condition, which can be candy edges, hedges, depth, line art, poses, etc. And we are asking the generate model to generate an image according to the image input condition. How we evaluate the controllability of the generated model is that we are comparing the similarity between the input condition and the detected condition from the generated image. We're using the metrics such as SSIM, RMSE, or MIOU for that. Here we have a background for the controllable generation, which is the ControlNet. ControlNet is actually a lightweight adapter that enables the controllable image generation. So basically, we have a pre-trained diffusion model, and we copy a the pre-trained diffusion model as a trainable copy and add some zero initialized convolution to stabilize the training. So the input conditions such as candy edges are extracted by the copied diffusion model, which we call its control net. So the why it is lightweight is that we only copy the encoder part of the diffusion model, so it is actually a lightweight adapter. And ControlNet++ improves the controllability of ControlNet by adding a consistency loss. So we have a one-time sampling during training to get a x0, which is the image estimated image latent, and we decode it with the decoder to the image space, and we detect the condition from that and compute the pixel level cycle consistency loss with the input condition, so that the controllability is explicitly improved via such a consistency loss. Another important background is the diffusion DPO, which contrasts a winning image and a losing image so that the model prefers the winning one over the losing one. Our motivation is that the one-step sampling in ControlNet++ can only be applied to small time steps, such as time steps smaller than 200, but there are a total of 1,000 time steps in the diffusion process. Applying diffusion DPO can generalize to all the time steps by preferring the winning image over the losing image. However, it first needs to ensure that the winning image aligns better to the input condition to improve the controllability. And it also needs to ensure that the winning image has a better quality. Otherwise, it introduces noise to the quality aspect during training. The first one is easy because when we generate image with diffusion models, we can always find the winning image that is apparently much more aligned with the condition. However, the second one for the quality is hard to guarantee because it is because even with some filtering mechanisms such as image reward score, we can not guarantee that there is no artifact in the winner image and the overall quality of the winner image is better. Another issue with the diffusion DPO is that some conditions are hardly observable in the raw image. For example, the candy edges, we can hardly observe the candy edges from the raw images. Our question is how to generalize a better controllability result to all time steps without introducing noise to the image quality. Our proposed method is the condition preference optimization, which directly contrasting good and bad conditions instead of images. Image input remains the same when we train the model. So we have an input image and we detect the condition as a winning condition, which it serves as the input condition. We can also call it the ground truth condition. And we generate a image from the ground truth condition, which is and we detect a losing condition from the generated image because the generated model is never perfectly controllable. So we are contrasting the winning condition and the losing condition with our defined CPO loss, which is derived from the diffusion DPO training. With our method, with our training method, our model achieves the best controllability among all recent state-of-the-art method, and we can see comparing to the ControlNet++, which is our comparing baseline, we achieve a significant improvement. And the image quality is also not changed when we apply our CPO training. We also conduct an ablation study regarding the Dyno V2 adapter because Control AR reveals that the Dyno V2 adapter improves the controllable generation with autoregressive model. What is a Dyno V2 adapter? Is that it is used to extract the input condition and feed it into the control net. So after the zero convolution, we add a Dyno V2 adapter and a further zero convolution so that it is send it to the trainable copy of the control net, and the result shows that the controllability and the image quality are significantly improved in most tasks. So here we have some qualitative comparison for the hedge and canny task. We can see that our method achieves the best controllability. Here we have a qualitative comparison for the depth and segmentation mask. We have comparisons for the pose, human pose, and line art. And for the segmentation mask, we show some additional demo. An additional demo for the human pose. For the hedge task, for the line art, for the canny edge, and finally for the depth. Thank you.